To get XAML, we'll solve some practice problems on the concept of support vector machines. For a linearly separable data set, the margin width between two classes in SVM with weight vector W is, you already know, this is the optimal hyperplane. These are the hyperplane for support vector. So this distance we assume it as 1 unit, this distance 1 unit. This is my hyperplane. Okay. So we try to maximize this, that is distance between them margin. We try to maximize this margin, that is the concept. So that is given by 2, 1 plus 1, 2 divided by the norm vector W. So this is the answer. Which of the following statements about hard margin SVM are true? In hard margin, it assumes the data is perfectly linearly separable. Yes. So this is true. That is the assumption. It can tolerate noise points inside the margin. No. So if this is the margin, these are the support vector hyperplanes, and this is the optimal hyperplane. So in hard margin, we are not allowed any points here. This is strictly not allowed. Whereas in soft margin, it is allowed. So this cannot tolerate. It minimizes W square, that is the weight, subject to strict separation constraint. Again, separation constraint is required, and it minimizes this. So what is that we are minimizing? We are minimizing 1 by 2 W square. This is what is minimizing to obtain optimal W and B. It is equivalent to minimizing hinge loss with C, this hyperparameter C, that is the penalty hyperparameter, approaches infinity. Yes. For soft margin support vector, we write it like this: C into proportional penalty zeta I. Okay, this is the how much violation it has created and how much penalty it has to pay. So as this value approaches infinity, so it acts as the hard margin. Next, the decision boundary for linear SVM classifier is, so already know this is the hyperplane equation for the linear decision boundary in SVM. Increasing the parameter C in soft margin SVM leads to, so we are trying to minimize this plus your penalty term, that is regularization parameter. So this is what is we are trying to minimize. So if I increase this value, so it tends to be, when C increases, it tends to become hard margin support vector machine. That means what? Misclassifications are not allowed in hard margin. So for example, this is my the initial hyperplanes, support vector hyperplanes and the optimal hyperplane. If in hard margin, there will not allow misclassification points here. In this margin, no points are allowed. So as C becomes greater, the penalty, that means what? I am reducing the margins, because if there is a point here, then the new support vector margin will come here. So the margin will be reduced in if there are misclassification in hard margin. So it narrows margin and fewer violations. No, there will be no violation here. So that is how C changes. If you increase C, that is penalty term, it acts as the hard margin. If you decrease this, it allows misclassification and then it acts like soft margin. So wider margin and more violations, no. No change in the margin, there will be change in the margin. Randomly wider or narrower margin, no. Next. Consider two classes with overlapping Gaussian distribution. Which classifier is likely to generalize better? So they are saying Gaussian distribution, the data follows the Gaussian distribution and the data are overlapping. Overlapping means, so the two classes are not so much of separable. So for that, hard margin will not allow misclassification. So it is not correct. So you can use soft margin to solve this. Perceptron is not the concept of the decision boundary, so it is not true. And also same thing for the decision tree. Which of the following is true for non-linear SVM with RBF kernel, radial basis function, that is Gaussian kernel, that is given as k of x I comma x is equal to e power minus some gamma parameter Euclidean distance square. This is the kernel, RBF kernel. So now the data is explicitly transformed into higher dimensional base. No, the kernel function uses the trick. It will do it implicitly. It will implicitly take the dot products. It will not calculate all the ordered terms. So this is not true. The kernel function computes inner products without explicit transformation. Yes, that is the kernel function. It is equivalent to polynomial regression. No, it is equivalent to your Gaussian kernel. It fails when gamma is large. So if this gamma value is large, this gamma is nothing but what? It is given as 1 by 2 variance sigma square. So if it is too large, it leads to overfitting. It may not fail. It will not fail. It leads to overfitting. Smaller gamma value is underfitting. That is, bias will be too high. Here variance will be too high. So it will not fail. It may lead to overfitting. The hinge loss function in SVM is defined as, so in hinge loss will occur in your soft margin SVM. So hinge loss is nothing but this violation, how much violation each data point creates, theta I. So this is, how can you find this? This is nothing but, see, we have our constraint as yi, that is class. It can take +1 or -1. Then we have W transpose into X plus B. This is equal to 1. This is the constraint minus this theta I for soft margin. So they are asking what is the value for this? What is the range it can take? So you can just rearrange it to get 1 minus yi into W transpose into X plus B. So this 1 minus yi is nothing but your f of x. So we already know that this zeta I cannot be less than 0. It can take 0 or can be between 0, 1. Okay. Or it can be greater than 1. So this indicates what? Misclassification. That is, it is on the other side of the boundary. It means wrong classification. This indicates it is on the margin but on the right side of the margin. See what it means? In this soft margin, so this is my entire margin. So this belongs to class -1. This belongs to class +1. See, if this zeta I equal to 0, that means what? So this is well within this class. So this is fine. If it is greater than 0 and less than 1, strictly less than 1, then it belongs to somewhere here. Okay, somewhere here. So this is my zeta I, this length, and this actually is 1. That is what we are writing, 1 minus zeta I. So that means what? It is on the wrong side of the margin. See this, it has to be here, but it is in this margin, but still on the correct side. So till this point, what? It belongs to class 1. Till this point, it belongs to class -1. This is +1. So that is the meaning of this 0 to 1. So somewhere here. So 1 is this. This is 0. This is 1. Again, this is 1. This is 0. This is 1. So length will be 1 here. So when this lies between this is the case. If it is equal to 0, then it belongs somewhere here. This is no violation. This is violation but still accepted because it is on the correct side of the margin. If it is greater than 1, that means it belong to somewhere here or here. So it is on the wrong side of the margin. That is the meaning. So it can take 0 to 1 minus this value. So this is the correct answer. In SVM dual form, the Lagrange multipliers alpha I correspond to non-support vectors R. So in the Lagrange multipliers, when you get it, so W will get it as, after optimization, I alpha I phi I class into xi dot psi. Okay. So this alpha I is a Lagrangian multiplier. It indicates if it is equal to 0, then it is not a support vector. So please refer to my video lectures. I explained in depth. Not a support vector. If alpha I is greater than 0, then it indicates a support vector. So what they are asking, non-support vectors, alpha I will be 0. For a 2D data set with points, they are given these points. Find the equation of separating hyperplane using SVM. These points we need not require because they are already given this W. So W is equal to, the weight vector is 1 comma minus 1 and intercept is B equal to 0. So you will write the equation as W transpose into X plus B is equal to 0. So W transpose, well, for X, let us take it as X1, X2. So this is 1 minus 1 into X1, X2 plus B equal to 0. So this will be X1 minus X2 is equal to 0. The dot product. So that is the equation for your hyperplane. If all training samples are multiplied by constant scalar k greater than 0, then the margin in SVM will, what they are saying. So this is the initial situation. Say there are support vectors here. This is a class minus 1. This is class plus 1. And this is my optimal hyperplane. Now this is my margin. If say there is a point xi here, okay, so if I increase this to kxi, some multiply by some constant to all the data, so how will my margin change? So that is proportional to, right? So this is what we are trying to minimize. If I increase this size, means the data value will increase, so the margin looks bigger, right? So it is again multiplied by k, so it increases by k. Which kernel can produce infinite dimensional feature mapping? So RBF, that is Gaussian kernel. Which of the following condition must be true for the optimal separating hyperplane in a SVM? So this is directly constraint they are asking. So this should be true. So again, when you optimize the dual problem, this should be also be true. Then the dual problem formation, all the support vectors, the Lagrange multiplier summation of all into the class be equal to 0. Then only I can solve the optimization problem. Otherwise I cannot solve. So this is also true. 0 is less than alpha is less than C only for support vectors. C here is coming from your soft margin. So what exactly this means? 0 less than alpha I is less than is not for support vectors. Because alpha I equal to 0 indicates support vectors. So this cannot be greater than 0. This is not true. If two support vectors are equidistant from the decision boundary, what does it imply? The margin is symmetric, margin is asymmetric, hyperplane will shift, slack variables will become 0. See, that is the basic concept of SVM. So this margin is symmetric always. The distance between this plane, this support vector and this support vector on the other class, this distance is always 1. So it is symmetric. Both sides it is symmetric. So this is true. Given a data set perfectly separable by multiple hyperplanes, SVM will choose. So the basic concept of SVM is if there are multiple hyperplanes separating the data like this, there are multiple hyperplanes possible. So what is the goal here? I have to choose one that maximizes the margin. Out of all the hyperplanes, I am choosing one that maximizes the margin. The maximum margin. Which of the following loss functions is used in soft margin SVM? So that is nothing but hinge loss. If C, that is penalty regression hyperparameter, is very small, SVM behaves like, so it becomes like SVM, that is, sorry, soft margin SVM. So it leads to underfitting. Again, I am telling C, to increase C, it becomes like hard margin. So that is overfitting, too complex. It can capture noise also. If C is low, it has underfitting, more bias. Okay. So it acts as underfitting. When using an RBF kernel, which hyperparameter combination is most likely to cause underfitting? So underfitting means C is small and then gamma is also small. So small c and small gamma. The soft margin support vector introduce slack variables zeta I. What does zeta I equal to 2 imply for a data point? So this is again zeta I. So this is a class +1, this is class -1. They are support vectors and the hyperplanes. And this is my optimal hyperplane. Zeta I, this is length is 1 unit. Zeta I equal to 2 means what? Suppose it belongs to this class and zeta I equal to 2 means 1 plus 1, 2. It is lying on this hyperplane on the wrong side. So it lies exactly on the margin? No. It is correctly classified but inside the margin? No. It is misclassified beyond the opposite margin. This is the true answer. It has no effect on the loss. So there will be a penalty. There will be a loss. If the weight vector is this and intercept is given as 3, find the distance of point 2, 3 from the hyperplane. So they are given W is equal to 2, -1, P is equal to -3. So how will you solve this? So already you know distance, that is D, is equal to length of this hyperplane equation divided by the norm vector. So now you calculate this equation. So they are already given this intercept and everything. So let us say this is 2, 1 into dot product 2.23. So x is given as 2, 3. So plus my intercept is -3. So this dot product is 2 into 2 minus 1 into 3 minus 3. So this comes out to be 4 minus 6 minus 2. What is W? Norm vector. W is equal to square root of these values. Euclidean distance. Not Euclidean distance, norm. So 2 square plus minus 1 square. So this is equal to √5. So this value I got it, mod of -2 divided by √5 is the distance. So this is 2 by √5. For a linear SVM, they are given this constraint for support vectors. If and W is given as 1, 2 and intercept as -4 and a point xi is equal to 1, 1. So which class it belongs to? So we already know this. So f of x is equal to the sine of W transpose into X plus B. So this is 1 comma 2 dot product X is 1 comma 1 for Xi plus B. B is given as minus 4. So this is, you take the dot product, sine of 1 plus 2 minus 4. So this is equal to minus 1. So the sign is minus. So it belongs to class minus 1. A data set in R square means 2 dimension in real space, has 10 points perfectly separable by multiple lines. How many unique maximum margin hyperplane exist? There may be any number of hyperplanes. It is, you can have hyperplanes like this between two classes, any number. Okay, what is that I am doing in SVM? I am trying to find the maximum margin. So there will be only one maximum or unique maximum margin. So the answer is 1. For a linear SVM, the separating hyperplane is given by this equation. Hyperplane equation is given. Compute the perpendicular distance from the origin to the hyperplane. That is again, they are asking the same thing. So perpendicular distance from the origin to the hyperplane. So origin means X is equal to the data point 0, 0, they are given. So what is W here? W is equal to 2, 3 and B is equal to minus 6. From this equation I am saying, how will you get that? It is W into X plus B. This is what we are doing, right? 2, 3, X1, X2. If I take, so this will be 2x1 plus 3x2 minus 6. Okay, is the equation B. So from this point they are asking the distance. So again you calculate the distance. D is equal to W transpose into X plus B, length of this divided by length of the norm vector. So length of this is so you substitute length of 2, 3 into, from the origin they are asking 0, 0 plus or minus 6 intercept divided by square root of 2 square plus 3 square. So this is minus 6 becomes plus 6 divided by square root of 9 plus 4, 13. So 6 by root 13. If the weight vector of linear SVM is W equal to 4, 3, compute the margin width. So already know margin is given in SVM as 2 divided by length of this vector, that is 2 units divided by square root of 4 square plus 3 square, that is 2 divided by 16 plus 9, 25, square root of 25. This is equal to 2 by 5 or equal to 0.4. For a soft margin SVM, a point violates the margin by 0.8. Find the slack variable theta a value for that point. So what they are saying, a point violates the margin. There is a point, this is margin is 1. Let us say there is a point here. This violation they are saying is 0.8. This is nothing but my violation, zeta I for that. So zeta I is equal to 0.8 only. For a polynomial kernel, k of x comma z is given like this, xz plus 1 whole square. Find kz for x equal to 1 comma 2 and z equal to 2 comma 3. So polynomial kernel they are given like this. So this is nothing but 1 comma 2 dot 2 comma 3 plus 1 whole square. I need not, that is the kernel trick here. So I need not expand this like polynomials. I can just use this dot product and then get the final value. That is the kernel trick. So 1 to 2, 2 plus 6 plus 1 whole square. So this is equal to 9 square. Given the decision function f of x equal to sine of this, determine which class f of 1 comma 1 belongs to. So the given w is equal to, you see here, it's a hyperplane equation. W is 2 comma minus 3 and intercept is plus 1. They are asking for this point, that is new point x1 comma 1. So we will write f of x, x is the new point, 1 comma 1 is equal to sine of w transpose into x plus b. So this is 2 comma minus 3 dot 1 comma 1 plus 1. So sine of this. So this is 2 minus 3 plus 1. So this is equal to 0. So what 0 means what? So neither positive nor negative. If it is plus 1, the sign is positive, then I will classify it as plus class, plus 1 class, otherwise minus 1 class. So 0 means it lies on the hyperplane margin, hyperplane. So what it means? So these are my support vector hyperplanes. This is my exact hyperplane. This point is lying on this self, neither this class nor this class. That is the meaning. So this is the equation of the hyperplane they are given. For an RBF kernel with gamma equal to 0.25, the square distance between two samples d square is equal to 4. Compute the kernel value. So k of xz is given as e power minus gamma, the Euclidean distance square, xi minus x whole square. So this minus gamma is given as 0.25. This distance square already they are given. Euclidean distance square, d square is 4. So this is e power minus 1 or 1 by e to 0.3679. What to get? Consider the following data set which is linearly separable. They given the data xi, yi and the support vector information alpha I. Compute f of 1 comma 1 and predict the class labels for the point x equal to 1 comma 1, that is 1 comma 1 only, and the given bias is 0. That means intercept is 0. So what is that you have to find? You have to find for this new point, find the sign in which it belongs to. Is W transpose into x plus b. So if you observe here, what is this dual condition in optimization says? Your alpha I yi, the summation should be equal to 0. Then only I can solve this optimization problem. Previously in one problem you saw the same thing. So first check this whether it's possible or not. So this will be 1 into 0.5 minus 0.7 plus 0.2. So this is 0. So this I can optimize this data. I can find the optimal hyperplane for this data. So now find the W. W is equal to summation of I alpha I yi xi. So here there are only three values they are given I. So this is alpha 1 y1 x1 plus alpha 2 y2 x2 plus alpha 3 y3. Substitute those values. This is 0.5, 2 comma 1. So y1 is plus 1. So is 2 comma 1. So alpha 2 is 0.7, y2 is minus 1. So minus 0.5, x2 is 0 comma 1 plus 0.2, y3 is plus 1. So then x3 is 1 comma 0. So if you solve this, we will get as 1.2 comma minus 0.2. So b is already given as 0. So sine of 1.2 comma minus 0.2 dot product with 1 comma 1, that is the new point. This x is 1 comma 1 plus bias is 0. So this is sine of, you get it as 1.2 minus 0.2. So this is plus 1. So it also belongs to, since the sign is positive, belongs to class plus 1. Consider the following soft margin SVM dataset with C equal to 0.6, that is penalty regulation hyperparameter is given as 0.6. The SVM solution has weight vector W equal to 1 comma minus 1 and the intercept is 0.5. Check if the point x equal to 1 comma 3 violates the margin. So with this data, you can find the first hyperplane. So how will you find the hyperplane? Or you just check directly the zeta value, calculate the zeta value. I will calculate the zeta value. So zeta I is equal to maximum of 0 comma 1 minus y I into W transpose x plus e. Okay. So now for this you need to calculate. No, they are already given W. They are given x and then b is given. So you calculate W transpose into x plus b is equal to is 1 comma minus 1 dot x is 1 comma 3 plus 0.5. This is 1 minus 3 plus 0.5. This is equal to minus 2 minus 1.5. So now zeta I is equal to 0 maximum of 0 comma 1 minus of minus 1.5. So we get it as 2.5. So 2.5 means what? It is on the other side. See, if zeta I is greater than 1, that means it is on the wrong side of the boundary, completely on the other side. So if you have a line like this, so if this is class 1, this is say class minus 1. From here, if a point is somewhere here, okay, so this is they are saying zeta I. So this is beyond this margin also. If it was here, then you would have classified correct classification. So it has crossed the boundary, so it is misclassified. So it violates the margin, yes. And then you also calculated the zeta I value. Hope you enjoyed the problems. Thank you for watching. Please like, subscribe and